Okay, so you guys have already done this, right? Pages 602, 603 in the textbook, label the microscope, read over the microscope skills section, and if you haven't done that right now, that's not a big deal. And that's what I've put up coming out of the textbook, or similar to it, with all of the important parts. And at this point, I want to label these so that you guys have all the correct answers. So without taking too long, and hopefully I don't make them up, hopefully I don't mess them up, because I want to get going to eventually into the lab, and we are running out of time. I'm going to attempt to give all the answers here, and I'm risking it because I'm recording this, so I could screw this up. This is considered the, and did you guys put eyepiece or ocular lens? Ocular lens, awesome. Ocular lens, excellent. That's ocular simply means pertaining to the eye, all right? So ocular simply means the eye, and that's where you look into. And the ocular lens typically has a magnification of ×10, all right? So most ocular lenses will magnify something by 10 times, all right? And ours definitely does that. As we move down, I believe this is called the body tube. Did I get that right? Body tube, awesome. And the body tube is simply a hollow tube that separates the ocular lens from the lenses at the bottom, the objective lenses, all right? This type of optical device needs some distance in between the two lenses so the magnification can work. I believe this one's called the revolving nose piece. Revolving nose piece. Uh-oh, my spelling terribly is going to come into play. The revolving nose piece contains the objective lenses, and it allows us to switch between various magnifications, all right? The shortest lens is the weakest. It tends to be ×4. It's written on the side. The next shortest is the medium power objective lens. It tends to be ×10. And the largest one is the high power objective lens. So this long one would be high power objective lens, all right? And it tends to be ×40, all right? ×40. We'll talk about the magnification more tomorrow when we get into more depth. This one to me looks a little shorter. This would be a lower power. It could be the low one, the shortest one, or it could be the medium. I'll just put low power objective lens. All right, and if it is the low power, ×4. Okay, and we'll talk about how they get together to give us our magnification. This next one down here is called the stage. Is it called the stage? The stage, and that is where our specimens go. We put them on slides, and that slide goes on the stage and gets secured by the clips, and they're called the stage clips. I'll go to the other side and I'll get those now. The stage clips, all right? So those are the stage clips. They keep the slide from moving around. All right. Moving down to the next one. What is the next one down there? What do we got? What's the next one? Yep. The diaphragm. And if you want to spell it right, you've got to say diaphragm. All right. You got to say it like that, or you will miss the G if you sound it out like I always do. So it's a diaphragm. And that is a specialized device that can open and close, and it allows different amounts of light in. All right, okay? Because, well, what's the next one? I'll talk about the diaphragm here in a moment. What's the next one down? What do we got there? Yeah, what do you got there, Grace? Yeah, the light source. Now, the light source on ours are mirrors, and they're terrible, right? You need to be close to the window. It's no good. So we've done different things for light sources. What I've done in the past is I've had students take their phones, turn on that bright flashlight, and put it down there, right? That's great. But it produces lots of light. It can be too bright. So you need to adjust the diaphragm so it's nice and small so it restricts the amount of light that comes in. And you can probably see the diaphragm on this one. It's just made up of different sized circles, which kind of prevents the light from getting through. Sometimes that's still too bright. What I get students to do is I get them to take a tissue, then put it over top of their phone, and that dulls the light again some more. Okay, awesome. Down here at the bottom, I grabbed the wrong pen, that would be no good. Down here at the bottom, we've got the base, all right? And I don't really know what around the corner here this is pointing at, so let's assume it's the base as well, okay? Working my way up the back side, this particular thing right here, I believe is showing us on this old one, this bolt here, which allows the microscope to pivot back and forth. It's not really on any of the other pictures. I'm going to just put here a pivot. All right, it's a pivot point. It allows it to bend back and forth. All right. This guy's the arm, and when we carry it, we hang on by the arm and the base so we don't drop it. This guy is the fine adjustment knob. All right, the fine adjustment knob. If you want to spell it right, you got to say it right. And that moves it very little bit. We use that one when we're under medium and high power. And this one up here is the course, and I always spell it wrong. Did I get the right course? Is that the right course? Oh, that's like a meal or something? I don't know. Oh, and now I've screwed it up. Oh my God. Is that better? Course? Adjustment knob. See, all these words, they cause me stress. Okay, and the course adjustment knob moves that body tube up very quickly, up and down. And that's how we find the focus when we're under low power. It gets us to find that spot nicely. Okay, let's keep going and talk about then, and I've described the functions to you, so now let's see if we can come up with the parts that have these particular functions. So, this is the lens that initially magnifies the image. Yep. Now that's an interesting take on it. I've debated this with students on this handout. You're saying it's the objective lens, right? Down close at the bottom that you're going to use initially. Yeah. Now I'm going to argue that we're going to put something else there, but I like the way you're thinking, and I'll tell you why. Yeah. The ocular lens. That's what I want to put as the answer, but I really don't like the question because I like the way you're thinking.
Well, because it doesn't initially magnify it.
Correct.
Yeah. Okay.
Yeah, so there's another one in here that's going to be our objective lens. Final magnification, all right? And I'm going to put here ocular, and I don't like these descriptions because I know what you're thinking. You're thinking, there's light coming from this specimen, right? And you're following the light up, so it magnifies first, right? And then, but if you're thinking of it like you're looking down, it doesn't really, now that's why I don't really like the way this one describes it. So, like I said, I like the way you're thinking because when I initially did this sheet, I thought, I like that idea, but you could think of it the other way. So this is really kind of ambiguous. The large structure that provides stability to the microscope. Yep, the base. It rotates to move each objective lens in place. Jess? Oh, goodness, that's no fun. Yeah, Jay? Revolving nose piece. Oh, revolving nose piece. Uh-oh. Okay, you get the idea. What's my next one? Supports the ocular and transmits the light. It supports the ocular lens, but lets that light through. What do you think, Ryan? Body tube. Body tube. Body tube. Provides rough focusing. Jay? Coarse adjustment knob. Coarse adjustment knob. Moves only a very small amount to provide a sharp image. Small amount. Ellie? Fine adjustment knob. Fine meaning fine, very tiny. Fine adjustment knob. Controls the amount of light that passes through. Controls the amount of light that passes through. Yeah, Jenna? The diaphragm. Diaphragm. Trust me, when I say that out like that, I'm spelling it. It's hard work for me. Final magnification of the object. I'm going to go with objective on this one. Objective lens. All right. And the reason I went with that is because it says final magnification of the objects. I'm thinking of that as being close to the object. You see what I'm saying? But you could argue it either way. You could argue it either way. Provides the light. I got this one. The light source. It's the light source. Light source. Used to carry the microscope. Yep. Marshall? Arm. 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 It is English. It's just not good writing. Holds the slide in place. Yep. Ryan? Sorry? The stage clips. Yeah, go ahead. Yep. You want to put arm and base? We've got base there as well. Arm / base. I'm good for that. I like that. You got the last one there, sir? The stage. The stage. Okay. All right. Okay. You'll notice the next part on that sheet deals with magnification. In my great planning mind's eye, I thought we could burn through that in no time. But it's already, actually, you know what? It's 2:05. We have no chance of getting to the lab now. Let's keep going and talk about magnification right now. Then we'll just do the whole lab tomorrow. How does that sound? Excellent. Good. Let's keep going with this document. Are we okay to keep going with the document since we're rolling? All right. So let's now talk about the way the microscope magnifies things. All right. You've probably all held a magnifying glass. All right. Now, these devices are made of lenses. And lenses are essentially transparent material, like glass or plastic, with at least one curved surface. There has to be a curve on that in order to bend the light. So if you have glasses, you'll notice they're curved. They've got curves to them. If they weren't curved and they were flat, they'd be windows. And they wouldn't magnify anything. They've got to be curved, okay? When you put two magnifying glasses together at the right spot, you can get a real super magnified image. I don't know if you've ever tried such a thing. And when you do that, the magnification multiplies. You get the magnification of both, and you multiply their powers, okay? So when we want to determine how much something will be magnified, all right, and I'm jumping ahead to here. Now, if you go down on your document, does it say magnification on your document? So we're going to just keep going with this. It looks a little different than this, but I want to keep going on your document. I want to keep filling it in. This is going to be kind of your note. So when you magnify something with a microscope, and it's called a compound microscope because it's made of two lenses, you take the magnification of the ocular lens and you multiply it by the magnification of the objective lens. So, under low power, by the way, that stands for magnification low. That's what that M(l) stands for, magnification low. Well, I told you the magnification of the ocular lens at the top. Does anybody remember it from when we were writing it down? Yeah, Grace? So, it's 10 times, or times 10. That's the ocular power. And does anybody remember what the low power objective power was? And I had you write it down. Yeah, Jack? Times 4 times 4, which means the overall power of low is times 40, or 40 times. 40 times bigger, okay? 40 times larger. Medium, again, the ocular is not changing. I might have mentioned the medium, but we didn't write it down. Did you hear me mention it? Jack? Yeah, it's a times 10. It's a times 10, okay? And therefore, how strong is the medium? We can multiply that, I hope. Times 100? Times 100. And under high power, again, it's times 10. I know there's a lot of times in there. Let's get the idea. Times 40. Times 40 equals times 400. So 400 times. Okay? All right? Now, I was going to get you guys on my next slides to write this next stuff down, but because you've got your document out and I just want to keep going, we might not write it down. We'll worry about it. I want to keep going on that next calculation that you have at the bottom of the sheet. So what I want to talk about, what I want to talk about now is what we see when we look into a microscope. If you've looked into a microscope, when you look down in there, what shape do you see? When you look into a microscope and you look down and you're looking at something in the microscope, what shape do you see? Yep. You see a circle, right? Have you ever done that before? You noticed that it's a circle? That circle has a name. That circle is called the field of view. That's the area that you can see, okay? Now, when you go to higher power, it's like you're zooming in on a little spot on that field of view. So things change a little bit when you zoom in to a higher magnification. Now, my pictures here in my little example are not circles because I couldn't find any circle ones online. So don't worry about the shape being a square, but you could imagine that this being an American penny under low, right? So that's under low. And then we might have something that has a revolving nose piece that maybe has 4 lenses. And here we get higher and higher, and this would then be under its highest power, okay? Now let's think about what we can see. When you change to a higher magnification, all right, when we go to a higher magnification, you see more of this and less of this. I want you to think about that statement. What can we see more of under high magnification? What can we see more of? What do you think? Details. We can see more detail, all right, but less what? Yep, Ryan? Less area. Excellent. Less area. So what we gain in terms of details, we lose in terms of being able to see a wide view. All right? Okay? So it works like this in terms of area. If we have a high magnification, what happens to the amount of area we can see? As the magnification goes up, what happens to the area? Jack? It gets small. We end up with a small area. And in math, when one thing goes up, and that causes a different thing to go down, we call that an inverse relationship. In other words, it does the opposite. When the magnification goes up, the area goes down. Okay? This is going to allow us to calculate the diameter of the field of view. We already know that ML stands for low magnification. Okay? All right? Now I'm going to tell you another symbol, DL. All right? And I don't know whether that's on your chart there or not. DL is the diameter of the field under low. All right? Okay? So if I have a circle here representing my low, the diameter across that field is dl, the diameter under low. And its magnification under low, well, it's times 40. All right? Okay? If we zoom in and we want to find the diameter under high, that's an H, diameter under high, and use the high magnification, which is 400 times, we need kind of an equation to get this. I apologize. You guys are writing. You're doing a fabulous job. You're doing a great job. I told you not to write, but you are writing. You're doing great. I'll go over this again, but I want to use this time right now to explain it. And if you did get it written down, that's great. And if you didn't, I'll explain it again. But since we're already rolling, it makes no sense to stop. Okay? So if I want to figure out what that diameter is under the high, I can create an equation where the equation does the opposite. All right? So if I have a ratio, the magnification, all right, under low divided by the magnification under high, I can get a ratio that tells me how much bigger or smaller that is. Because it does the opposite, right? Because when the magnification goes up, my diameter goes down. It's got to do the opposite. My other side of the equation has the diameters in a ratio, but it does the opposite. So what do you think I'm going to put at the top in terms of diameter if it does the opposite of the magnification? Look at the way I've got the letters oriented in this equation. Magnification low over magnification high, the diameters do the opposite because they are related in an opposite fashion. What am I going to put with this D? Jack, what do you think? I'm going to put a DH over DL because they do the opposite. That's an inverse relationship. Okay? Now, I know I've got some of my math people that don't like math getting a little nervous again. You will have the equation. You won't have to create this equation. I'm just kind of teaching you about it. We sometimes want to find what that diameter under high is. Does anybody know how to manipulate an equation to get a variable by itself? Anybody done that type of a thing? If I want to get the diameter under high and I want to move this DL to the other side of the equation, what do I have to do that? And again, depending on who your math teachers were, what do you think? Jewel, what do you got? Cross multiply, some teachers called that. Some teachers might say that you multiply both sides by DL, so times by DL times by DL. In the end, when we move this guy over to the other side with what you might have been called cross multiplying, we have DL times, what did I do here? This could be a catastrophic failure. Something's not looking right. DL, ML, MH. What did I do? It's an inverse relationship. I've got them on opposite sides. DL. There's a screw up here. In the end, that's the wrong equation. I have to burn this video, or other teachers will watch it and make fun of me. What have I got wrong? I can't see it. I've got to stop this video. I've done something horrifically wrong here. Let me just stop this and take another look at this. Oh, tab, stop this video. Stop it. No, we'll leave it. I'll post it. I'm okay. I'm okay making mistakes.